And our next speaker is my colleague from McGill, Kartiek Agarwal, who will talk about Majorana zero modes and dynamical decoupling.
So first of all, thanks to the remainder or other organizers for giving me an opportunity to speak today. So I'm going to talk about doing dynamical protocols with Majorana zero modes, in particular dynamical decoupling protocols. And so off the bat, I'd like to acknowledge, first of all, my principal collaborator on this work that I'm going to talk about, which is Ivar Martin. And also, we've had very useful discussions with my colleague Tammy and her student Bill Chuang at McGill, and also my master's students Brett Min and Bastian, who are working on extensions of the ideas I'm going to talk about today. And so the main references for what I'm going to talk about are these two works that were published last year. Okay, so I'm going to start with the dynamical aspect and talk about driving quantum systems more generally before I move on to the Majorana aspect of things. So please bear with me. So I want to talk first of all about what happens very generally if I try to drive a quantum system. And in particular, many-body quantum systems. So I'm imagining a situation in which I have a Hamiltonian, there's a base Hamiltonian, and then there's a perturbation, and the perturbation is time-dependent, which is periodic in time. And so the first thing you can ask yourself is, what happens to the energy?
Many angles, from pop culture to how we talk about women who quote-unquote marry up.
Okay, so what happens to the energy density of the system as a function of time? And so you can examine this stroboscopically in time if you just evaluate the Floquet unitary, which describes the time evolution of the system over one time period. And so suppose you start in the ground state of your system, so it's some vector 1000 in your Hilbert space, and you repeatedly apply this Floquet unitary to evaluate what the system does at stroboscopic times. And so, of course, what you expect is that this 1 is going to be converted to 1 minus epsilon, and these excited states are going to be, filling up as time goes on. Eventually, of course, approaching randomness. Now, in particular, if this Floquet unitary or this, over one course of time period, if the dynamics are extremely strong, if you're in the strong driving regime, what you're doing is you're making local rearrangements of whether you have a spin system, so you're flipping a bunch of spins. If you have an electronic system, you're carrying out local rearrangements of the charge. So if you're in the strong driving regime, then you expect that over the course of one time period or so, you're going to increase the energy by an order of magnitude of h, which is whatever the local energy scales or couplings you have in your model. And so as a result, your system is going to heat up very, very quickly. And this is, certainly also what you'd expect from your understanding of statistical mechanics. If you have a many-body system and particles can exchange energy with each other very well, and you're driving the system, it's going to keep heating up, and eventually all energy states are going to be equally explored. You're going to go to infinite temperature. So obviously that's bad because at high temperatures, there are no interesting correlations. So the question is, can you ever use periodic driving to engineer quantum systems, especially many-body quantum systems? And so over the last decade or so, we have come, across many examples where, in fact, periodic driving doesn't lead to immediate heating of a quantum system. Okay? So there are many different settings in which this works out. But the one that I'm going to be focusing on is this very general setting that was elucidated by Abanin and company and this group, Japanese group, which is that if you drive a quantum system at a frequency that is slightly larger than the local energy scales of the system, right, then in fact the heating time can be exponentially large in the frequency divided by that local energy scale h. Okay, again, local energy scale means whatever rearrangements cost about the energy h. And so the way to explain this very, very long time scale is to think about it as follows. You're effectively inundating the system with photons at a frequency omega. And to absorb a single photon, which will cause heating of the system, you need to make many, many local rearrangements of the system. Okay, and of course that becomes a very high order in perturbation theory process, and as a result, you get an exponentially long heating time. Okay, so under the very general setting in which you're driving the quantum system at a frequency that's larger than the local energy scales, you can expect that there's a very, very, an exponentially long thermalization time. And so that long thermalization time in principle doesn't mean that there's no dynamics within one time period. So you can have a situation where your system is completely, being transformed over the course of one time period. But over the, stroboscopic times, your dynamics is described by some effective Floquet Hamiltonian that is conserved for an exponentially long time. So really, you can think of HF then as an effective Hamiltonian that describes your quantum system's properties. And so the natural question then becomes, in this Floquet system, can this HF exhibit a richer set of symmetries than the parent Hamiltonian? And if so, then there's a whole set of broken symmetry phenomena that can emerge that could not emerge in the equilibrium context. And so, without digressing too much, this is exactly, for instance, what happens in the case of a time crystal, where Floquet Hamiltonian develops an additional symmetry which gets spontaneously broken and shows up as this time crystalline order. So anyway, the time crystal is maybe a very, very esoteric goal for this driving. But there's a very simple reason why you would want to, say, develop symmetries in your quantum system by doing this strong driving. And so the simple reason is, suppose you have a Hamiltonian H that is composed of a bunch of different terms, and a set of terms B, which again can be decomposed into B1, B2, and so on. And all these terms B, you don't want to exist in your Hamiltonian because they take you away from the interesting physics that you'd like to have in your system. Okay. So how do you want to? How can you get rid of these terms? Okay. So one way to get rid of these terms is to imagine driving the system with a set of unitaries x1, x2, and so on. Their main property is that they essentially flip the sign of these terms, B1, B2, and so on, okay? So the Majorana connection will be that these x1 and x2s will be realized as Majorana operations, and we'll come to that. But for the moment, these are, generic Z2 symmetry generators that effectively flip the sign of the terms of the Hamiltonian that you don't like. Okay. So very simple thing. Let's try driving the system by applying x1, this unitary transformation, periodically to the usual time evolution of the system. So what I'm imagining is I'm, evolving the system with its own Hamiltonian H for some time period t0. Then I hit the system with x1. Again, I let it evolve with its parent Hamiltonian H for another time t0, and then again I hit it with x1. And of course, if you expand this, what you can see is that, half the time the system is evolving with the Hamiltonian A plus B, and the other half of the time the system is evolving with the Hamiltonian A minus B, okay? So on average, in fact, B sort of cancels out if T0 is sufficiently small. And so in particular, all the terms in your Hamiltonian, effective Hamiltonian, that do not commute with x1 become of the order of T0 times H. So H over the driving frequency. Assuming you're driving at a large frequency, this is some number or less smaller than 1. And so you can continue doing this by what we call fractaling. So you can take you were driving the system with x1 at a frequency 1 over T0, but you can also try to then drive it as well at frequency 1 over 2 T0. So there's a self-similarity in the protocol. And so if you stick in the Floquet unitary at 2 T0, you put in x1, you can convince yourself, in fact, that the terms that don't commute with x1 become further suppressed to, square of t naught h. Okay, and in particular, you don't have to drive the system with just x1. You could drive it with another, operation x2, which will reduce those terms d2 that you don't like by an order. Okay, and so the natural question you ask is, well, can we continue doing this procedure endlessly? And so the answer is no, because as you keep driving the system at lower and lower frequencies, it's easier for the system to absorb energy and heat up. And so the heating time reduces significantly as you keep, adding more fractal layers to this protocol. And so we can basically, what we'd like to do is maximize an effective timescale on which these operators x1 and x2 become effective symmetry generators of the system. That is, they commute with your Floquet Hamiltonian and the heating time at the same time. So once you try to maximize both these quantities, one realizes that there's an optimal number of fractal layers, which is related to the frequency of the driving. And so this is really my last slide on this, a more general point. So here, we are examining a system numerically via exact diagonalization. This is a Majorana chain, and we're driving the system with certain operators, x1 and x2. It doesn't really matter what these are, except that they're global operators. They're not simply local operators. And we define a memory function, which basically tells you if this operator has relaxed in the system or not. So if it's 0, then that means that operator is conserved. And if it's 1, it means that the operator has relaxed. So if you look at this left plot and you're driving the system just with some, you're looking at the relaxation of some local observable, which is not, meant to stay conserved, then it relaxes fairly immediately on a microscopic timescale. But if you look at operators, these global operators, x1 and x2 that you're driving the system with, then they in fact do not relax for whatever exponentially long time. And so really, suggesting that your effective Floquet Hamiltonian has developed these additional symmetry generators. Okay, and so you can also look at, the value at which this, saturates, which tells you how well the operators have relaxed and how well they serve as symmetry generators. And you can see that as you increase the number of fractal layers, first, things get better before eventually getting worse. So there's an optimal number of fractal layers, which is some finite number. Okay, so that's the most that's the general discussion. The key points being that you can take your many-body system, you can drive it stroboscopically with a set of operations which become effective symmetry generators of the Floquet Hamiltonian. And then you can work, of course, with the Floquet Hamiltonian as an effective Hamiltonian for an exponentially long time. So what is the connection now with Majorana fermions? So by the way, this class of protocols that I've described, in various forms and shapes are known as dynamical decoupling protocols in the NMR literature and elsewhere. So might as well call this dynamical decoupling. And now the key point here is that these operations, which flip signs the terms in your Hamiltonian, these can in fact be implemented very, very nicely with Majorana zero modes. Okay, so why is that? Well, this comes from just a very simple property of Majorana fermions, right? If you take two Majorana fermions, gamma I, gamma j, and you try to exchange them exchange them twice around each other, well, they return to their original position. So gamma I and gamma j return to their positions. But additionally, they acquire a minus sign, which is topologically robust, okay? So, as long as they're really zero modes, they're very, very far from each other, there's no dynamical phase. The only sign that comes is this topologically inbuilt sign, which is this property of Majoranas. Okay, so one way to, of course, see this is, with the example that people have been talking about of these p-wave superconductors in which vortices bind the Majorana. fermion, the vortices, of course, are associated with the superconducting phase jumping around them by, or winding around them by 2 pi. So as you move one vortex around the other, the phase, the vortex has to cross essentially the branch FET associated with the other vortex at some point. And in this process, the Majorana, associated Majorana, is going to acquire -1 sign. Okay. So as a result, this is, really it's a topologically robust additional phase that you get. And now it's kind of obvious that with these Majoranas, they're really special from the perspective of dynamical decoupling. So for instance, suppose I have a generic Hamiltonian that's parity conserving, made of these, multiple Majorana fermions. So I have some term which hybridizes the Majoranas, 2 Majoranas. There's some interaction term between 4 Majoranas. And what I do is I double braid, or, we've also called this braid, and I don't know if this term will ever catch on, but we double braid these 2 Majoranas repeatedly, periodically in time. So for instance, suppose I, leave all the Majoranas aside and double braid gamma 1 and gamma 2 with one another. So as a result, they're going to acquire a robust minus sign every time period t0. And so if you look at your Hamiltonian, the time evolution is going to be described by, for instance, these set of terms for one time period, and another set of terms in which something like a gamma 1, gamma 2 term does not flip sign, but a gamma 1, gamma 3 term indeed flips sign, robustly changes to -1. So if you do this periodically in time, terms like J13 should become reduced in magnitude. So another way of putting the same thing is that if I look at the effective Floquet Hamiltonian, then the braiding operation, which is this unitary gamma 1 times gamma 2, becomes a symmetry generator of the dynamics, and where it commutes with the Floquet Hamiltonian. In particular, there's nothing stopping us from taking these x's, as I discussed from the numerics in the last part. There's nothing stopping us from having, doing these multiple braiding operations involving pairs of Majoranas at the same time. So x, x1, x2, and so on, these can be multiple, these braid operations performed with many, many pairs of Majoranas. Okay. So that hopefully addresses why Majoranas are special for implementing these protocols. And now you'd ask, okay, well, what is this really good for? So there are a few problems, current experimental problems, and there's so many systems, so I'm not going to speak about all of them, but certainly in the quantum wire and maybe the planar Josephson junction devices, it's clear that the Majoranas that one realizes are that they're somewhat fat, which means that if you take your wire and the wire is like 1 to 1.5 or 2 micrometers long, the Majoranas that you realize are actually a significant fraction of the wire, and so they overlap and hybridize with one another. That's exactly what we'd like to avoid. So that's something that I'm going to talk about how we can try to improve on with this with these protocols. And to some extent, people have started using these residual couplings to imagine many of these wires in some pattern on a 2-dimensional plane, realizing all kinds of effective Hamiltonians. And there as well, you can imagine that the main constraint of kinds of Hamiltonians that you can realize comes from the geometry, because the distance between these Majoranas effectively sets the kind of hybridization terms you can have. And so you'd like to ask if there's ways of removing or at least reducing some of these geometric constraints. And lastly, of course, one of the challenges is if we do realize all of this, how are we going to end up braiding Majoranas? And so, of course, there are many thoughts. And in fact, Floquet has also been applied to this question. So I'm not going to go too much into this. I'm going to focus on these two particular areas and ask if these dynamical decoupling schemes I just discussed can improve the situation for these kinds of problems. Okay, so I said that the double braiding of these Majoranas is the fundamental unit I want to work with. The problem, of course, is that double braiding is hard. Braiding is hard. It hasn't been demonstrated experimentally as of yet. So can we do this somehow in a way without actually, how do we implement this really? Is it just, so luckily you can implement these double braids without actually physically double braiding Majoranas. And it turns out that the process is as robust as, the -1 that you get is as robust as you would get if you actually physically double braided Majoranas. Okay, so let me give the setting that I'm thinking about. So again, I have this quantum wire, and I have two Majoranas on this quantum wire at the ends, and these are fat Majoranas. They overlap with one another, and I'd like to reduce the hybridization between this gamma L and gamma R. So of course, if I try to say, imagine just theoretically for now, if I was able to double braid gamma L and gamma R, then of course both these gamma L and gamma R are going to flip in sign, and as a result, the Hamiltonian, which the hybridization between them is not going to oscillate in time, so it's not going to be reduced. So what I really need is some sort of external Majoranas. So of course, one thing we can do to solve that is to just bring a quantum dot. Assuming it houses a fermionic mode, and of course, every fermionic mode can be decoupled into two Majoranas. These are not zero modes, but this is certainly theoretically sensible. And so now one thing that could work is if somehow I was able to double braid gamma 2 and gamma L repeatedly. In that case, gamma L times gamma R is going to flip-flop in sign in time, and that's going to effectively reduce this hybridization between gamma L and gamma R. So, of course, I can't actually physically double braid these two Majoranas. This is actually sitting on the quantum dot and completely bound to its partner. But luckily, the only thing I really actually need to do is flip-flop the parity of this quantum wire in time, because precisely the parity operator is precisely this I gamma L gamma R, right? And so if I'm able to flip-flop this parity operator in time, then I can effectively make this term flip-flop in time and reduce the hybridization between the n Majoranas. And so to do that, the simplest thing is to just vary the potential on the quantum dot and make Landau-Zener tunneling of an electron to happen back and forth between the quantum dot and the wire. That, of course, will change the parity of the wire repeatedly and achieve the objective goal. So now, of course, you naturally ask, well, is this Landau-Zener transition as robust as physically double braiding Majoranas in giving minus signs and so on? And the answer, luckily, turns out to be yes. And so the way to think about this is as follows. When you do a Landau-Zener transition, you can have non-adiabatic errors. So you can imagine going from one parity state to another parity state accidentally. And that, of course, you can suppress with exponential accuracy, like, as long as your Landau-Zener parameter is in the right regime. The other kind of error you can imagine is phase errors. So you can also accrue dynamical phase as you time evolve the system as it's coupled to the quantum dot. And what you can show by careful reasoning is, in fact, that the phase that you acquire, the dynamical phase that you acquire, is in fact exponentially small in the distance between gamma L and gamma R. Okay, so in other words, you need at least quasi-good Majoranas in order to be able to do this repeatedly. But if you do have quasi-good Majoranas, in principle, you can improve the situation further. Okay, and just to make this assert this similarity between the robustness of the Landau-Zener transition and the robustness of the physically double braiding Majoranas, if you had two Majoranas, their hybridization, of course, would depend exponentially on their separation. And as you drag them along one another, they would also acquire dynamical phase precisely proportional to this hybridization, times the time it takes to do this operation. So that's exactly the same thing that happens in this case as well. And so really this thing, is as robust as doing double braids with Majoranas being dragged around one another. And so this is what we did. We went ahead and numerically just, plugged in a Kitaev chain coupled to a quantum dot, driven periodically in time. And so, in units here, one is essentially the local energy scale. The Majoranas initially were hybridized in this particular case by some energy that's 10 to the minus 3 of the initial of the local energy scale. And as you drive, you can come down to hybridization of the order of 10 to the minus 5. So much, 2 orders of magnitude smaller. And in principle, you've now come up with other protocols slightly more complex than this that can actually reduce the hybridization by many, many more orders of magnitude. So let's see how I'm doing on time. I guess I'm okay. So you can also show that the best case bound in this case for how much this Floquet Majorana hybridization energy is compared to the static hybridization energy is precisely given by the same exponential factor that describes the robustness to noise of the original static Majoranas. So that's exactly the same bound with which you can reduce the hybridization in this particular protocol. Okay, and the reason you have a sort of a lower bound is really because, and this is something I didn't maybe discuss clearly, but the protocol involves an electron jumping from the quantum dot to the quantum wire. If the parity of the wires, if there's already an electron being occupied in these two Majorana modes, then in fact what happens is that the electron and the electron already on the wire go together into the bulk. And so these two tunneling processes, one conventional tunneling, one Andreev tunneling, have slightly different amplitudes, in fact, and that's what makes this protocol not perfectly efficacious in reducing the hybridization, the static hybridization between the Majoranas. Okay, some other important things I want to mention, and one proposal. So the Majoranas, one thing that we hoped was that in this whole process, the Majoranas that we come up with after driving them are going to become more localized. But if you look at the IPR, which tells you how localized these modes become, they don't actually become much more local. So that means that it may suggest that the noise sensitivity is not improved by this driving, except that in some sense the two modes become orthogonal to one another. They don't become more localized. So that's obviously not as good as it could be. But one thing to keep in mind is that this protocol, the way you can think of this as like a spin echo protocol, okay? And so what it does is effectively it eliminates particularly low frequency noise, any noise below the frequency of driving, which couples to this parity operator. And in particular, actually, we can make these. Okay, one thing I didn't mention here is that the Majorana that is flipping sign is the one coupled to quantum dot. So it's actually flipping sign by itself. And so, a lot of the noise that couples to these operators will be reduced. And in particular, if the main source of noise is, this electromagnetic 1/f noise, which one believes to be the case, then there will be certainly a huge impact of this protocol. The other thing we know is that this only works with, Majoranas or quasi-Majoranas. So you need somehow decent Majoranas to begin with to be able to do this dynamical decoupling technique. So one simple proposal to go ahead and check if you really realize in a quantum wire two bound Majoranas at the ends of the wire is to do this driving and see if the coherence time of the putative qubit really reduces because of the suppression of this coupling to 1/f noise. And so that should only happen really if you have bound Majorana states at the ends of the wire or quasi-Majorana states, but not these very localized on one end Andrea bound states and so on. So like I said, the final thing, like I said, you can imagine more elaborate protocols which reduce the hybridization by 5 orders of magnitude. How does this work for tetrons? I believe there should be something very similar. A quantum dot shuttle charge between two wires now. So there are a few other things that we're thinking about. How what happens to conductance measurements in this particular case. All right. So with this, I can propose a new sort of architecture where I have multiple quantum wires, but then I also have quantum dots associated with each, 2 quantum dots with each wire, 1 for each end Majorana. And if I ever want to double braid, say gamma 2 and gamma 6, all I need to do is turn on the quantum dots on those respective Majoranas, and that's going to effectively flip their signs and perform this periodic double braiding of these 2 Majoranas. So in principle, if I had a bunch of these wires on a 2-dimensional plane, and I could drive the system in the right way, I could hopefully realize the larger class of Hamiltonians than would be otherwise permissible by the geometry in which these wires are laid out. So this is just one example of how this can work. So suppose you have a bunch of these Majoranas, and they're all quasi-Majoranas. They overlap with one another. They're laid out in a 1-dimensional plane. You can go ahead and engineer Majorana end modes by doing the following. So you double braid periodically gamma 2, gamma 3, then gamma 6, gamma 7, and so on. And if so what happens is that these Majoranas that are being double braided, they flip in sign in time, and this divides this chain into 2 subchains. And if you look at these Kitaev Hamiltonians enough, you will naturally realize that in fact one of these subchains has a weak odd even bond, the other one has the opposite, and so one subchain is topological and one is in the trivial phase. So one subchain will have a very nice 0 mode that in principle, it will in principle be some kind of a superposition of all these Majoranas, but it should be a 0 mode. The important thing is you need to reduce the coupling. It's not that you're trying to completely eliminate any coupling. Just this kind of driving this even odd effect can give rise to this phase. And then you can take the trivial subchain and drive it with another set of double braids, exactly analogous to the first situation. And you will divide essentially this subchain into 2 sub-subchains, one of which is topological, one is trivial. And again, so as a result, you can realize more and more 0 modes at the ends of your chain in which you started out with imperfect 0 modes. And you can see this also numerically. Okay, so I think in the interest of time, I'm going to continue without discussing that in more detail. So what else can you do with this? Well, if you want to build a quantum memory, your ultimate objective is to make the Floquet Hamiltonian exactly 0. So if you check the right set of symmetry generators for whatever arrangement in which you have your Majoranas and their hybridization, you can try to effectively eliminate all the couplings. And so in a case where you have completely all-to-all coupling between these Majoranas, and you drive this with a set of n symmetry generators, n is the number of Majoranas, you can effectively engineer a perfect degenerate subspace where you can take any operator and it lasts essentially forever in time, or to an exponentially long time until the system heats up. You can create SYK, you know, one doesn't have to just do periodic double braiding. If one is a little bit more creative, and this has worked with Falco-Pientka, you can imagine killing all quadratic couplings between Majoranas, leaving quartic couplings behind. You can imagine, again, you know, doing something similar with 2D models. If you have a 2D arrangement of Majoranas, trying to realize other non-abelian excitations, maybe this is something we're still thinking about. Okay, yeah. So I think that's basically what I wanted to talk about. Maybe I'll just take a minute to summarize before I get your questions. So the first thing is that, you know, you can drive a many-body quantum system as long as you drive it at large enough frequencies. Then, you know, in principle, the heating time can be exponentially long. If you're dealing with real materials, this may be a bit harder, but if you're dealing with these quasi-Majorana modes even, or completely, you know, artificial quantum systems, then this becomes much more possible. Majoranas in particular are excellent for dynamical decoupling, Majorana zero modes in particular. And so I propose this kind of a new architecture where you have quantum dots associated with quantum wires to help, you know, to utilize this to you know, improve the kind of the hybridization between Majoranas in current generation of wires, quantum wires, and yeah, okay. So what beyond these double braids? You know, double braids are only this, you know, single class of universal, you know, single component of the universal gate set. You have to implement all these other interesting gates. So it would be nice if you could find, you know, dynamical ways of doing them robustly as well. As we somehow discovered in this case that, you know, Landau-Zener transitions do the job for these double braids. Okay, so that's all. Thank you very much. I think I'll stop here.
Thank you, Kartiek, for this nice talk. If people have questions, you can ask them in the chat, or you can raise your hand and I'll hopefully see it. Okay, maybe in the meantime, I'll ask a little question. So at some point you show that you want to have a quantum dot coupled to each Majorana.
Yeah.
Can you arrange to couple to a single Majorana? Because sometimes two Majoranas are really on the same site. Are you thinking
so
of
I mean, like I said, it kind of relies on having the, you know, these quasi-Majoranas where on the wire, they're somewhat they're separated, they're still at the ends, even if they overlap considerably. And then you can, in principle, address each of these Majoranas individually by, you know, having a quantum dot that couples to that end of the wire. Within the approximation, you know, that I've laid out, this e to the minus L over psi factor that figures everywhere.
Mm-hmm, mm-hmm. And there's a question from Bert Halprin. Do you want to ask your question, or should I read it?
I was worrying about end effects, time end effects. In other words, if I understand what you're doing, if I have two Majoranas that are far apart and they're coupled by some amount, and now if I repeatedly flip the parity of the wire, I can reduce the effective coupling by a very large amount. That's actually, I think, exponential, if I understand it, in the rapidity of your spin flips, if it goes on for an infinitely long time. But if I have to suddenly stop it at some finite time in order to read the memory or do something with it, won't I then get a smaller reduction due to some kind of fractional time at the end where the spin flip hasn't been complete?
Right. So that is a very good question. I mean, I guess there has to be, okay, so these are I think these are all interesting and difficult questions to understand. So once you do this Floquet business, you get a Floquet Hamiltonian. How do you actually read out things? So my guess is that there should be some way of, adiabatically sort of slowing down this dynamics or reading in information, or alternatively, as long as you address the qubit only stroboscopically, then you don't have to ever stop this periodic driving. So yeah, okay, I think that's a very good question. I just, that's something that has to be fleshed out, and I haven't really fleshed it out completely. And similarly, things like, if you have a Floquet Hamiltonian, how does the system relax to, say, if I have, couple it to a bath, does the Floquet Hamiltonian itself mean like there is going to be relaxation to the ground states of the Floquet Hamiltonian and so on? That's also, again, quite unclear, and it's more complex. It depends presumably on the kinds of dissipation you have in your system and so on. So I don't know the answers off the top of my head to that to that question, but I think these are all things to think about. Yeah.
Of course, in practice, a power law might be good enough. I'm just reducing things by a factor of 10 may be good enough. You don't maybe need e to the minus 10. But I also, I guess, it is a little bit related to how accurately you can, if you can do things truly stroboscopically, you're all right. But if you make some error in when you do your readout, then you have the same problem. But
that's
again,
right. So topology doesn't protect you from that, for sure.
Great. Okay, so there's another question from Roland Willa. Do you want to ask your questions, Roland?
Yes, hello. I had a question. So you were describing how you can get rid of terms in the original Hamiltonian with this scheme. Can you also have an algorithm that induces term in the Hamiltonian that were not present initially?
Yeah, so that's a very good question. And I mean, I think the point is that you can, but these terms will come generically with a 1 over frequency denominator. In some sense, if I just in a very trivial example, why can't I turn my? Yeah, I can. So if I just go back to, for instance, this here, right? So essentially the Floquet Hamiltonian is mostly A, and then I've generated some extra terms. These are quasi-local in that they come with their commutators. So they retain a notion of locality, and I can, in principle, generate higher order terms. And like I said, they're going to come with a denominator of the frequency. So they're a little bit suppressed. But they can be important, especially if you get rid of all the, that can be one way of engineering terms that you want. There's some limitations to this as well, which I'm thinking about if there are ways to improve on. So one limitation is that if you start with, say, somehow a non-interacting system, or a system that's largely non-interacting, then the effective Hamiltonian will also mostly be non-interacting. Is there a way of engineering interactions in this way? That, I think, is something that maybe one has to be a little bit more clever and not do periodic driving, but maybe there is some way of doing that, and that's something to think about as well.
Thank you very much.
Thanks.
Okay. Thank you. We should move on, even though there might be a few more questions, but we can save them to the discussion session.